Hey everyone, I'm Christopher Glyer,
And I'm Nick Carr.
and this is State of the Hack. And we're going to have a special focus today on data scientists. We have Matt Berninger with us.
Hi.
And we've talked a lot in the past on past episodes about data science and how we incorporate it into our products and our services and a bunch of other pieces.
Probably got some things wrong, so we thought we'd have a.
I slept at Holiday Inn Express last night, but I'm not a data scientist. Fortunately, this guy might be one.
No, I am.
Okay. So Matt works on our advanced practices team currently with Nick and team. And I don't know, why don't you give us a little bit about your background, what you do, and maybe how you got into the industry?
Cool. So I started actually not in cybersecurity. Coming out of college, I worked in the financial industry as a quantitative analyst for a financial firm. And that was interesting, but as I learned about the cybersecurity industry, I thought that was a problem that I felt motivated by the mission. And so I went over and worked at the Department of Homeland Security, US CERT.
How did you transition from finance to, what were the things did you do to get from, finance to?
Got it. It was not really, I basically quit my job in finance and was able to, luckily, through some folks that I knew just from the DC area, get an interview, essentially,
Okay.
Working as a contractor for DHS. I originally started out, I believe, in the budget office for a couple weeks.
Okay.
And then got moved into the cybersecurity office, and from there just kind of fell in love with the mission. And worked my way into the SOC and started working sort of, botnet threats, DDoS threats at the time. They were all the rage. And so that was always interesting to me, but I kind of kept a mathematical view of those things. So especially looking at DDoS threats, for example, looking at various different changes in traffic patterns was something that always intrigued me. So
You were there for the fun Iranian bank DDoS
Banking,
stuff,
yeah.
and so trying to tackle it in a
alleged. Yeah, that was a good time. That was that was a fun couple months for sure. And that actually, I think that particular campaign kind of got me in on more intense incident response work. So I got asked to help out with incident response and started working bona fide intrusion analysis with US CERT. Learned a lot, and then found out about the good work that was going on over at FireEye Mandiant, and came over there and started out in managed defense. So I was really interested in the managed defense mission, particularly because of the sheer amount of data and the scope of the work there. So I thought that was really cool, and I wanted to find ways to sort of actually try and stop bad guys from hacking. We were doing a lot of IRs back in the day, and they started to take on a familiar feel of, well, you got owned, the bad guys took everything, here's what happened, here's how you remediate. And I thought, well, wouldn't it be cool if we could actually just stop them, win one of these games?
Sure.
And managed defense seemed like a good opportunity to get in front of that. So in managed defense, I led what we call surge investigations or response investigations. And managed defense looks at alerts and activity at all of the clients. And when something happens, obviously we report it. But in a surge investigation, you actually go deeper and you find out if the attacker went interactive, and if they did, how far did they go? Did they move laterally? So it kind of takes on the feel of a small incident response.
IR.
It's a mini IR. If it becomes a much more larger IR, then it gets handed off to a team that can sustain that for longer. But because of that, I was able to be exposed to so many different types of responses, so many different types of clients, so many different types of time frames and networks. And so it was incredibly educational, and I really appreciated that. But because managed defense has such a large scale, we also had these optimization problems that, again, the math background started to come into play and say, okay, well, this is an optimization problem. We have a lot of work, not a lot of time, not a lot of people. How do we get more efficient? And through the tutelage of a couple various different mentors of mine, I was pushed towards what I now know to be machine learning models to solve these problems. And so it kind of pushed me in this direction to say, if I'm doing a lot of the same things over and over, any good computer scientist is going to think, well, how can I automate that? And for us, it was, if I'm making complex decisions about things over and over, how can I train a model to make those decisions for me? And so that's kind of what got me started. And started building models basically to solve managed defense problems. That moved me over to the data science team of FireEye, where I got to learn even more from really experienced data scientists like we have on the team here. And then from there, now I'm currently working with the advanced practices team to solve advanced practice problems using machine learning when appropriate, or data science. So that's what I'm doing, and I really like it.
Cool. So we thought it might be useful to, it's a artificial intelligence, machine learning are kind of the buzzword du jour in the industry right now. We thought it might be useful to give you, kind of the audience, a little bit of a background on some of the terms.
And us too. It's always good for a refresher.
Sure.
A little 101, a couple, maybe 5 minutes of what we need to know to digest some of the things we're going to talk about on the episode.
Cover everything in 5
So if you know this stuff, you can fast forward
5 minutes.
But
we're just going to talk a little bit about kind of what the basics are, what the differences between different types of machine learning and the pros and cons, et cetera. So
cool. So you mentioned AI. That's an acronym, or artificial intelligence is a term that gets thrown around a lot. I have found that I don't find it to be a particularly helpful term because it kind of means everything and nothing in many contexts. So
it's great for marketing.
It is, yes, it's very fun to say and think about. I've also found that in more technical circles, especially the data science, machine learning circles, AI generally means a level of complexity and cognition that many people would argue we haven't actually gotten to yet. General AI is a term that gets used a lot to really talk about something that really doesn't need a whole lot of hand-holding.
So it's like Skynet.
Yes, exactly. Skynet, yes, Skynet. And thankfully, or not, Skynet doesn't exist yet. So I tend to stay away from AI as a term.
Okay.
Because it's not very precise.
So pro tip, use the word ML if you're going to talk.
Yeah. And then I actually would like to talk about data science and machine learning. I think of machine learning, and some may disagree, I think of machine learning as a sort of a subset of data science. Data science to me is we have all this data in this industry and others, and making sense of it, that includes, data mining, just basic data analytics, data engineering, things that aren't even machine learning, but just managing and understanding data, getting insights from data, and making sense of it. That, in my mind, is data science. There's a wide range of subfields under that. Machine learning, to me, is basically a toolkit that fits the following paradigm, in my opinion. Conventional computer security, or conventional computer science, you give something an input and a program. So if I have a program that adds something by 3, I give it an input, it adds 3, and I get 5. Machine learning is I give something an input and the output, and it figures out what the program is. So the machine learning analog of that would be I give it a 2 and I give it a 5, and it figures out I think you should add by 3 to get there. Right? So when you have a problem where you have inputs and outputs, but you want to figure out how to get there, machine learning gives you the program or infers the program. And so that is sort of how I view it generally. I find that to be a useful model for viewing machine learning.
So we talk a lot about machine learning models. What's the difference between, what is a model and what are the differences between different types of
supervised and unsupervised.
Right?
Got it. So supervised machine learning models, for the term, are generally something where you have labels. So to use malware classification as an example, you have a binary, you have a sample, a file, and then you have a label. It is good or it is bad. And then if you feed lots and lots of these into a machine learning model, or machine learning algorithm rather, it will infer a supervised model that can help you determine an unknown instance and say, here's the label it should have. So basically, for shorthand, supervised models are trained on data with labels. Unsupervised models do not have labels, or unsupervised modeling. And they are generally intended to sort of understand the underlying structure of a data set. So for example, if you had a large data set and you said, I want to understand what are the topics in this corpus of information, you could do topic modeling or something like that, and it would say, oh, it looks like there are 3 or 4 topics, and here is why I think these things are one thing and these things are other things. Clustering is often used in conversations about unsupervised learning, and that will say, these things over here are all very similar, these things over here are all very similar. It won't apply labels to them. It won't say these are all this and these are all this. It'll just say these kind of hang out together and these kind of hang out together. So unsupervised learning can be helpful, but it doesn't have labels. The other separation that I like to point out in machine learning is the area of deep learning. Deep learning is very in vogue right now for a lot of reasons. The increased computation ability that we have.
Is that things like neural networks?
Exactly. So if you hear neural networks, deep learning networks, that's deep learning. And deep learning is actually not that new of a concept. but it's become much more effective because we can compute so much better now with our resources.
Yeah, I mean, I remember in college in like the early 2000s learning about, like taking class specifically on neural nets and being like, what's the point of learning about like, because you learn about how it works, but there's no real practical application of it because we didn't have computational power to actually deal with it at the time.
Exactly. And it's actually the computational power and the sheer amount of data that we're generating as a society and in various different industries. That has really allowed deep learning to sort of make a jump to a point where it's actually providing incredible accuracy, incredible results for things like machine vision and audio processing and complex problems like that. The difference in my mind is from a cybersecurity lens between deep learning and what is called traditional modeling is the occurrence of features. So features are how you represent the data. So going back to the malware example, if you were to pull out various different features about the malware, things like the PE header or the entropy or the size or things like that, those are not the file, those are representations of the file, and those would be features. So if you were to feed those into a model, you'd be feeding them into a feature-based model. Neural nets generally tend to learn their own features. One of the reasons this is important is because if you get the output of a supervised model, sometimes you want to understand why. If it says this file is bad, you might want to say, okay, well, that's cool, but why did you think that model?
It had this import hash, or like it was above this size and it was packed with this packer, and I saw these strings and this combination of factors. I think that's why I think it's
especially when you're making relatively important decisions based off of that, right? You may need to show your work a little bit.
Right.
When you don't have features, that can get more difficult. There's a lot of really interesting research trying to understand what neural networks are learning. We actually have a blog. It was written by Scott Kuhl. It's on the FireEye website. It's about what our CNN research into malware classification is learning.
And it's computational neural network, not the broadcast channel.
Yes. Convolutional neural network. And sorry. Thank you. But in any case, it's really cool, and it shows what the neural net may be learning. So that's a really great area of research trying to unravel the interpretability of neural nets.
So just letting this model loose on it and then trying to understand what it's decided. But we run these things in parallel?
Yeah, so we're doing that research in addition to having a traditional classifier, right? So we may be able to learn things from the neural net that says, oh, you might want to look into this as a potential feature. And so the interplay between those two approaches can be really interesting and helpful. But they are different. Traditional models generally are feature-based, and so you can ask it, okay, what's the importance of a given feature?
Yep.
And you can maybe have a bit more interpretability into why a decision was made.
So one of the themes for this show that I want people to get out of it too is if you see research on it, or definitely see marketing on someone saying we're using ML or AI, I guess is one of the preferred terms, what are reasonable questions to be asking? So I'm hoping, is it reasonable to ask if you hear someone's using ML, to ask even the number of things you've given here? Is this a supervised or unsupervised?
Yeah.
What
I guess a big piece is the data set.
Exactly. So I've done this a couple times, actually, just walking expo floors. You'll see a lot of companies that are selling machine learning or AI. And it's interesting to just ask and say, okay, well, what problem? I like to ask, what problem are you solving? Right? Because I see that there's a difference between desire and problem. A desire is, let's apply machine learning to network data. A problem is we have a lot of weak signals that we're applying to network data, but we have too many alerts to actually distill them into good and bad. Let's build a supervised or semi-supervised model to solve that problem. That's a problem. So that's question number one, is what problem are you solving? And then you should be able to get into, is it supervised, is it unsupervised? If it is supervised, what data set was it trained on, and where did you get those labels? Because the veracity of the labels can have a large impact on the veracity of the model. The model is only going to learn what you feed it. And so that's a very good question to ask. I would also ask if the model is dependent on third-party or external data to be trained, or if it's dependent on internal data for that company or that organization. So if I was an organization looking to implement machine learning, if that machine learning is going to be dependent on my internal data set, then I better have a pretty good understanding, a reasonable understanding of my own data set. To give you an example, if you were going to have an unsupervised anomaly detection model based off of network traffic for your organization, and you didn't already have a good inventory and understanding of your own network traffic, when you find anomalies, what are you going to do with them?
Right, because you need to basically say, yes, that is normal or not.
Exactly. You can find anomalies, but
I mean,
the
a
next
network
step,
is just it's one big anomaly, right? Like,
Exactly.
My experience usually is.
So the next step becomes very difficult if you don't have context, you don't have an understanding of your own data. Baselining a network that you don't understand is going to be very difficult in many cases. So that is one thing that I would separate is the model something that gets trained on my own data, or is it a model that is trained on external data and given to me? So most malware classifiers are the second type of model where they've been trained on a large data set of different files, and then when you apply it into your network, you're gaining all that information into that classifier.
Well, and that's partly possible, I assume, because of you can, as a vendor, buy access to, say, a whitelist from another vendor or the NSRL or something else, and you can also get access through various malware sharing networks to labeled bad data, right? So even as like a brand new startup, you can get access to labeled data.
Yep.
But it feels like that works well for the malware problem, but maybe not other classes of problems where getting access to labeled data is much harder.
Yeah, actually, that's very, very right. So I think one of the challenges in cybersecurity ML, when you compare it to things like image recognition, self-driving car research, which frankly is very, very far ahead of where cybersecurity is in ML. I'd argue that one of the reasons is the availability of publicly available data sets, labeled data sets. So if you're looking into ML research, you'll find things like ImageNet or ResNet. These are enormous data sets that are labeled, that are sort of canonical in the ML communities for testing benchmark models. So a lot of the cutting edge ML research will use these data sets to sort of prove their model's efficacy. We don't really have anything like that in cybersecurity. There are a couple great repositories. secrepo.com is really good. I've used that. But it's for lots of really good reasons like privacy and information sharing and frankly label noise. By that I mean what you call bad might be different than what I call bad. Right? But if
it's easier when it's like this is a dog and this is a cat.
Exactly.
And there are many good examples of like a cross between the two, but we all may have different. Somebody using PS exec in a way that might be bad in one context and not bad in the other one, or depends on a bunch of other factors, right?
So there's a lot more fuzziness around some of our labeling in this space, and that plus the privacy restrictions in many cases have limited the availability of public data sets. So it's really hard to get these massive data sets to do a whole lot of ML research on. And I hope that gets better. I think it is getting better, but it is sort of keeping things like very large neural net implementations or research from going forward. So yeah.
So yeah, it feels like a lot of the classic security problems we have also apply to ML, which makes sense. Like baselining, understanding what an anomaly is from a responder is a challenge, and so if someone's selling you that you're gonna, this will automatically surface anomalies or something malicious, it's reasonable to ask a little bit more questions.
Absolutely.
Yeah. Okay.
I would say that to give you an example of like applying a model to a use case, the first sort of set of models that I was building in managed defense was sort of a journey through that of, okay, we have the following problem. We have a lot of alerts and we want to be able to classify them quickly and we want to be able to make decisions about them. So the modeling itself was, and a lot of practitioners will tell you, the actual just running the machine learning model and getting it to sort of infer a model and give you one was relatively fast. The harder part was understanding our data set split, understanding where we might have biases, understanding how we're going to provide interpretability to analysts. So one mistake I made building a model was we were looking at all these different file write events, and the model was doing really, really well, and we were running it. We would do something called cross-validation. So we do a k-fold cross-validation, which essentially means you're running it over a couple different iterations of your training set. Almost all the time it was doing really well, except one or two times it would do really badly. So we looked at it and we said, okay, well, why is it doing really well most of the time and then sometimes really poorly? And the reason was our data set was almost entirely ransomware alerts with a couple non-ransomware alerts.
Like volume-wise, because
For file writes.
Yeah, because you may have 10,000 files written on one system, and they each generate an alert.
Yeah.
or code.
Right. So file extension includes .locked or something like
Sure,
that.
exactly.
So you're really skewed that direction.
So the model was like really good at ransomware, and then was applying basically a ransomware model to non-ransomware
Got
alerts. And so that's a good example of, hey, we have all of these alerts that they're the same type of alert. So at that level, we thought, oh, this will be our model for this type of alert.
So would you call that like overtraining or sample bias, or like
Yeah.
what would you call that?
It was
problem?
overfitting is a term that's used. It was overfitting to one particular class of example in that. And so when we looked at that, we said, okay, well, we definitely need to split these out. It's not generalizing well to the general problem. So what we ended up doing was saying, okay, this ransomware problem seems to be an easier problem to solve. Maybe that's not something we need ML for. Right? Another concept in ML is this idea of lift. And this is another question I would ask, is let's say you have a signature that is 98% accurate. You have a snort signature, you put it out, and 98% of the alerts that come back are true positive bad. Then somebody comes along and says, hey, I have developed a machine learning algorithm for the same problem that is 99% accurate. Well, that sounds great. 99 sounds good, but you actually only gained 1%, right? If the random chance is 98% and your model's 99%, you only got a lift of 1%, right? So sometimes when you hear these really high accuracy rates, you poke out a little bit and say, okay, well,
Is that something buyers or people considering it can ask? I mean, do people measure, provide lift, or that's something you have to assess for your organization?
I think for your organization it would be, because you'd understand better how your data is split. Also, if you have something called like class imbalance, right? Let's say your data set was 90% bad and 10% good. Well, if you train a classifier and it's 95% accurate, you have a 90% accurate classifier by just randomly selecting. If you train a classifier to just say everything is bad, you're going to be right 90% of the time.
Right.
So that would be an example. If you understand your data set and say, well, I'm already at 90% accuracy. One, maybe you don't necessarily need a machine learning solution to get where you want to go. And also, if you do, there may be a legitimate reason why 9% is just not good enough. 98% may be where you need to get. And if ML is going to help you get there, then great. But I think understanding the baseline can help sort of cut through some of these like 99.9% accurate solutions and say, okay, well, random chance has a 99% accuracy. So something to keep in mind.
Sweet. For just one quick thing, when you talked about that alert prediction model that you were helping build for managed defense, I remember walking past you and seeing you had like some Python scripts up at your desk. Now it's a standalone thing. You guys blogged about it.
Yep.
You and Wallen put forward, here's how our prediction model works here, and you guys gave some background on how you got to that point and struggles and stuff like that. But like for the average person, like what did you build that in if you wanted to do a little bit of ML tinkering at your desk? Like that's how that started.
Yeah, so I actually, first of all, say that the ML training community is fantastic. It's really, the resources are amazing. You can learn so much just online in various different sites like Coursera, Udemy, or what have you. Your chosen online learning platform has a lot of really good courses, and there are some canonical ones out there. The deep learning courses on Coursera are really good. But there's a lot of really good stuff. So I got into that. I originally wrote those models in R. For those who don't know, R is like a statistical language. It's a very high-level language. And by high level, I don't mean difficult. I mean it's abstracted at a high level. That was largely because I was a big math nerd, and it's very much a mathy language, and it's very statistical. So I wrote those in R. While there are Python modules for R, end to end, we were using a lot of Python. So I was quickly told, well, you need to rewrite that in Python. So I was like, got it. Time to learn Python. So I basically learned how to do that stuff in Python. And actually, in the recent years, the Python support for the ML community has been really good. So
got it.
You can do, I would recommend Python. That's not to say there aren't other great languages out there. Scala, R, people use these for ML. But
it seems like for people that want to get into it, we do a lot of like, someone proves out a concept, applies a model, shows that it works in Python, and then we'll hand it over to developers on our product side.
And they may move to some other language, I would also argue that like one of the dangers that I was warned about was this idea of just sort of like plug and play ML. And I got to say, I had great mentors.
You can't just sprinkle the ML on everything.
You can't just import sklearn and then just you're good. So I had really good mentors and people I worked with on the data science team, and they helped me learn this. And that is, You don't have to do the actual calculus for like convolution every single time, but it is important to appreciate and understand the intuition behind the algorithms. So one thing I have seen that we try to avoid here, and I certainly try to avoid, is just taking a machine learning algorithm off the shelf because I read about it in a blog, plugging it into my data set, and then believing the output. Right? If I don't do my due diligence of understanding that data set, understanding the complexity and the inherent biases and the potential problems with the model that I'm using, then I'm setting myself up for failure. Because when something inevitably goes wrong with that data or with that model, I'm not going to be able to understand why it didn't work. So I would recommend to people who are looking to get into it, do take the time to sort of learn the math behind the models. It can be very intimidating at times, but again, the resources out there are very open and sort of welcoming for people who may not have a formal mathematical background. There's still good intuitions you can learn. But I would caution against just sort of like download neural net package and like apply to data, because that can get you in trouble.
So what are some of the problems you've tried to solve here in your experience, and like how did you pick a particular like supervised versus unsupervised? Like,
Got it.
Which ones did you fail at, or you feel like you succeeded at? Like, I don't know. What's been your experience with that?
So I would actually point to a model I've been working on still. We blogged about a couple months ago. It's called atomicity, and it's a clustering algorithm or a similarity algorithm. And
You originally presented it as, what was the name of it?
the original name was AP Tinder.
Okay.
I honestly
Finding your
didn't.
perfect match.
So that was the name of the conference talk at CAMLIS. Also, for people interested in cybersecurity and machine learning, CAMLIS, the Conference for Applied Machine Learning and Security, is a fantastic conference to attend. And so I presented it last year at CAMLIS. And I honestly didn't think AP Tinder was going to get accepted, but then it did. They swiped right. Nice. So yeah, that was fun. But the actual name of the model is called atomicity. But developing that model, or really that framework, because it's a couple different things, a lot of time was spent understanding the problem statement. So the problem statement is that we have a lot, and you guys talk about it on this show a lot, we have a lot of these clusters of activity, and we're oftentimes trying to attribute that activity to a named group, somebody that we know. And so this becomes a document, or similar to a document clustering problem. So for example, if you were a librarian and somebody handed you a book with no title and no cover, no author, and you just had to figure out what section, and say you were organizing books by genre, and you had to figure out what section to put it into, rather than having to read the entire book and understand it and say, okay, this is a mystery novel, or this is a science novel, science fiction novel, you would maybe want to have an algorithm to sort of extract features from that book and then classify it accordingly, or put it into a topic accordingly. So that's what this does. We have these sort of like unlabeled things, and we want to know, okay, well, is this similar to other things that I have seen, and if so, why? And so that's what this model does. It takes the terms out of our sort of reports on these clusters, and then it weights those terms according to a couple different algorithms, TF-IDF, vectorization, and cosine similarities are similarity metrics. So for those of you keeping score at home, look those up. They're great. And it's all outlined in the blog. But essentially, it takes those and says, okay, this particular usage of this malware is very specific to this group, and there's only one other group that uses it. So we're going to say that they're similar for that reason. To give you a counterexample, if you were to say, well, this group uses phishing as a vector. Well, most groups, arguably all groups,
might be used once or twice.
Yeah, exactly. So that's a very common vector.
Right.
So you can't.
You're going to weight that lower.
You will downweight that, right? Because you can't say, well, these two groups are the same because they both use phishing. Right. But if there's one type of proprietary malware for which there is no source code or open source code, and you say these are the only two groups that have ever used this malware, and they actually tend to use it at the same time against the same victims, like that's a pretty compelling case that maybe these groups are the same. So that's what that model does. There is a supervised element as well to the model, which is we wanted to figure out which aspects of groups were more important and why. So is usage of malware more important than using the same methods or using the same comms methods? And so we trained a regression algorithm actually to set linear weights to tell us how to weight those accordingly. So it was a really fun project to work on.
And so the output of that then feeds to other folks.
Yeah, it was used
on
for
your team, right?
the APT 33 blog update that we were able to merge the other UNC group into there. It was interesting. It was like actually featured first. We were saying it showed us this was probable APT 33,
But we weren't
then over
sure.
time,
Right.
that the confidence increased. So it's been trained off.
So
of
how
those
we use it
decisions.
is, it's an input to a human to say, should I consider merging these two groups, or are they similar, or as you're trying to find like what is this and who's it related to? So
I'm happy to know people are actually focusing on making sure it's implemented right, because it's very blind for us, like just asking about a particular UNC group, the uncategorized cluster, and it says it's this similar to that, and it's cool that it's something constantly improved
Right.
and trained off of analysts. So like that's a theme I feel like that you've been pushing forward, being embedded on the front lines, is like making sure analysts are directly connected to a model.
Yes.
Or do you have tips there for?
I think that just a lot of times the data science or the machine learning will stop short of sort of the next step. So it's great to have a super accurate model, but especially in an area, discipline like cybersecurity, where you have to make decisions, you have to make them quickly, and you have to be able to back them up. Providing interpretability is paramount. Wallen's work on, and it's in our blog about the UAC models or the alert models, was great because that helps you get that last mile. Like if I show you a model that is, and I just tell you it's super accurate, you might trust me for a day or a week. But if you can't look into it and say, oh, I agree with the decisions that model's making and here's why, you may not use it. And usability is everything. And so that's definitely one. And then I would also say a certain amount of training for practitioners is super helpful. It's something we're doing here at FireEye. I really enjoy doing it. Bringing our analysts in and spending a day or 2 days with them and saying, here's the basic concepts of machine learning. We're going to demystify it for you.
Is that to increase their confidence in what you guys are doing, or to identify new problems to solve with it?
It's both.
Okay.
It's one, for them to be versant in some of these ideas, like a confusion matrix or a rock curve, understanding what that is and understanding why it's important. Understanding, frankly, the weaknesses in models and why models are going to be wrong sometimes. And even if they're wrong once or twice, it doesn't mean you should throw them out. And so I think just sort of like, again, taking out the shroud of mystery and saying it's not a magic box, here's how it works. But then, as you said, problem formulation, getting them to say, oh, you know what? That anomaly detection algorithm, that sounds really familiar to the way I think about this thing. And then you have a really good problem to solve. And then you bring that back to the data science team and say, okay, we have a problem here that we want to solve. So it works both ways.
So taking it from a slightly different angle, and I'm not sure if you have an answer for this or not, but like, are there either research problems where you've either tried to apply machine learning and realized that either you didn't have the right data set or it wasn't a good solution for the problem you're trying to solve, or like when it goes sideways, or like when you realize like how did you get to that point, or are there certain problems where you've run into where like actually I have this maybe this isn't the right tool to use to solve this problem?
Yeah, so I'll give you an example. We're currently doing some research. Stay posted. But it's on getting knowledge from paths, file paths. And our data set was okay, a couple tens of thousands of files, or file paths rather, and they were labels. So it was a supervised learning problem. So they had labels, good, bad, and we wanted to train a classifier. So we trained a traditional classifier using some features that we derived. And then I thought, it might be interesting to sort of treat a file path like a sentence. And so I started looking into sentiment classifications. This is a well-tread area in machine learning, but sentiment analysis, rather. And this is something that's used for online reviews and tweets and such. And so treating a file path like a sentence or a sequence, there's some models called LSTMs, long short-term memory neural networks, and they're rather complex. And so I thought, let me see how that works. So I spent some time sort of getting the data into a place where we could put it into the model, and the model went and it did its thing, and then it basically decided to call everything bad, and it overtrained. It just overfitted. And I thought, I might not have a large enough, diverse enough data set here. This is, I'm using a lot of advanced machinery here, but my traditional model is actually doing well enough, and it's not overfitting. but the neural net implementation was definitely overfitting. Not to say that there aren't some tweaks and changes and hyperparameters we could change to maybe make that work better, but that's an example where
That's cool.
you have a lot of code written, you have a lot of cool terms to throw around, but it just isn't working. So
You didn't get enough lift from that to...
It just wasn't, it wasn't working. The accuracy was okay, but it's still, when you poke at it, you say, okay, it's actually way overfit.
So a couple things we just wanted to hit before we close out the episode. There's been some, I feel like a lot of research. I know we've done some research on adversarial use of ML and some activity back in July that was caught a lot of attention for bypassing binary classification. And then wanted to kind of make sure we covered some of the upcoming research from the data science team.
Yeah, so we've done research into, well, first of all, adversarial ML is really nothing new. Since there's been sort of implementations of machine learning, there's been a lot of examples of trying to defeat it. If you Google that, you'll see an image of a bus, and then there's a static image that's overlaid, and then you can get it to say it's a toaster or something, right? You can fool ML algorithms, and this is something that's currently being researched. So it's not unknown that you can fool ML. It actually presents a pretty interesting attack surface, frankly. And there are a lot of interesting things going on there. So we did some research last year, and we're continuing to do it on doing adversarial work against neural net classifiers. So we published a paper last year on that, and we're continuing to do research into it. And yeah, I mean, I think that despite all of the marketing and all the hype about ML, sometimes it shocks people to know that it has weaknesses and it can be defeated. But as we found in everything in security, of course it can be defeated, and it's just another thing that we have to continue to improve on. So it's something we're looking at. I know other folks in the industry are looking at it, and I expect that in the next 5 years or so, we'll start to see more of this sort of adversarial cybersecurity research start to come out.
Yeah, it feels a little bit akin to the signature-based antivirus industry from, I think it's maybe a research paper 10 years ago on how you could use kind of packers, so you could pack a piece of malware that would flag antivirus, and then by packing it, you would then be able to evade that antivirus. And we didn't throw out signature-based antivirus; it has its place, but there are certain classes of ways you can target it, and in response, how different AV vendors have gone about that is actually unpacking or figuring out how to unpack samples and then run the signatures against those as a way. So there's kind of point counterpoint whenever things like this come up.
Yeah, not to get too far into like how we're doing it, but I know we're having a lot of fun and high return on watching like if this thing has a really low ML score but behaviorally looks very bad, that's also a signal.
Behaviorally in like a sandbox.
Yeah. If the execution does something really bad but the ML score is low, that might be indicating evasion. Like any other obfuscation or something where these things don't match. So I guess from my perspective, not building into the products, but like having a bunch of ways to measure activity, and ML being one of those or a driving force has been helpful, but having like checks in place. Yeah,
it provides an independent signal that you can use in combination with other signals to, try and get a leg up. But yeah, the cat and mouse game will continue. Cool.
And then you had last you had some I guess a side project you're working on with I remember you started this actually a while ago, but you want to tell them about your side ML project? So for my
New Year's resolution, I actually I promised myself I'd only interact with Twitter via the API, which has been healthy for me. It's been very healthy. But in any case, I thought it was interesting. I just wanted to learn more about social media analysis. It's something I think is really interesting. Information operations, I think, are a totally new, or maybe not new, but interesting aspect of cybersecurity. So I was like, okay, I just need to get versant in some of this. So I decided, well, I can't tweet as well as you guys can. So I thought maybe I'd just build a model to write tweets for me. So what I did was I pulled down a whole bunch of tweets from a lot of different accounts, almost all cybersecurity accounts, and basically fed into something called a Markov model. So another thing to look up, Markov process to basically build tweets for me. And so it's come up with some pretty good stuff.
What's your favorite?
My favorite is most computer security is just meat sugar. I believe that
At
was
some point, I think you tinkered with like overtraining on thought leadership tweets
Yes.
that were being categorized. Is that right?
Yes. Oh no, I leaned hard towards thought leadership. I didn't want anything that people would actually think was useful cybersecurity information, lest they chase down an MB5.
I love that you built it. He was looking at like trying to see how our team was looking at open source stuff and what was really valuable, and like how to help us surface that, like identify what was interesting and have us label what we thought was interesting. And then we had way more fun with let's actually just look at thought leadership and auto-generate tweets about it.
In going through thousands of tweets to try and find the useful ones, by definition, you find the not useful ones, and so that was a fun data set to work with.
Yeah.
It's been
Imagine the pressure when he'll give you your score for how useful your tweet was for every single
You're doing
one.
all right. I'm monitoring.
Nick's at like a 2% level.
Oh,
like,
people like junk
Pretty
food.
good. It's
People like
pretty
it.
good. Yeah.
So no, perfect. And I think you're planning to submit that other places and hopefully present more on that. And I know we have some upcoming work. What's been behind us the whole time is some of the
Yes.
string sifter stuff. I don't know if you want to hit
So
on that
this is a
real
great
quick.
example of a well-defined problem. One of my favorite quotes is a well-defined problem is half solved, and this is a well-defined problem. And that is when you're doing binary triage or binary analysis. Our awesome Flare team brought this one to us, and they're looking through strings. And while they are able to do lots and lots of super cool malware analysis things, strings is still a great way to get started. So rather than scrolling through thousands and thousands of strings to try and find the interesting ones, they worked with Philip Tully on the data science team to do something called String Sifter. And that is a tool that helps them prioritize strings of interest, the most interesting strings that they may then use to further their malware analysis. So this is a great blog. Philip did awesome work on this, and I think they're going to present it or
The plan
release some
is
more
to maybe
stuff.
release it. So it's pretty cool because like that's what we're all trying to figure out on a detection engineering standpoint. If you're like writing Yara rules, you're just choosing strings
Right.
that you believe are
It's a good one.
malicious,
Right.
Exactly.
or tied to it, and this is a model to help people understand what actually is.
Yeah, so this could potentially surface a string that an even very experienced malware analyst might not have seen, and that provides value. And so it's awesome to see this stuff come out.
Cool.
Sweet.
Yeah. Any other papers or other things you want to hit on? Or
Not for me. You would know about them.
I'm excited in the direction that the industry is going. I think there's a lot of really good discussions going out. I think people are starting to see that machine learning isn't perfect. It isn't everything. It's not going to solve everything immediately, but it is a tool and a toolkit that can be used to solve problems. So I think it'll be cool to see where this goes in the next couple of years. And then more specifically at FireEye, I'm very encouraged with the talent and the interest and the connections that we have between our practitioners and our data scientists to solve some of these problems like String Sifter.
cool. Well,
Cheers.
thanks for your time.
Thanks, guys.
Great having you on. Catch you next time.